problems. The only thing that will be different in the quiz is I may have changed some of the values. But if you understand those problems, you should not have any problems with the quiz. But if you have questions, though, now's the time to ask your questions on any of those, because I'm about to move to the next section. Any questions? Okay, great. All right. Class, I want to thank you all for being in attendance on time. This is commendable. I also want to thank you for how you are submitting your assignments. And I hope that you are following along in your textbook or with the notes I'm giving you, or even if you're finding some other alternative resources, which is also good. Hold this 1 second. Hold 1 second. I got to guess. Hold 1 second. Okay, so today we're going to move to a new section, but before I do that, I want to review where we were last time, before I do that. Okay, so freely falling bodies. Before I share that, I want to, do you all see the free falling bodies?
Yes, ma'am.
Okay, great. Let me move back then. Okay, let's move to this page again. Oh no, I've lost my pen. Give me 1 second. Give me 1 second. I misplaced my pen. How many you want? Okay, class, thank you. I'm back. Now, before I go forward, I want to review these equations. So we said that the final speed, v sub f, is equal to the initial speed, v sub I, plus acceleration times time. Then we said the displacement, x, is 1/2 initial speed or velocity plus the final speed or velocity times the time. Or the final speed squared is the initial speed squared plus 2ax. And then our last equation says the displacement or the distance is the initial speed times the time plus 1/2 at squared. Now, that's how we wrote those equations. So if you look here, on the equation quiz, let me find the equation quiz. Hold on, I don't see it on my screen. Let me. Okay, give me a second. Sometimes this whiteboard is not easy for me to manage. Okay, give me 1 minute, class. It's my information is not coming up. Okay, a new share. Okay, do you see this page with write the following equations? Do you all see these?
Yes.
Okay, great. Now the last one that I wrote said that the displacement, okay, hold on. Okay, the displacement, we said x was the initial speed times time plus 1/2 acceleration times time squared. Now, that works when we know the initial speed, but also I left a space here for displacement if I know the final speed times time. So that is minus 1/2 AT squared. Now this particular one is not used as much, but you can still have it in your notes. The only difference is if I know the final speed instead of the initial speed, rather than adding this expression, it's subtracted. So now I'm going to move to the next section, which talks about free fall acceleration. In other words, rather than having motion along the x-axis, this is x, now my motion is vertical. And for vertical, of course, that's my y-axis. So I'm going to use these same equations now, but going forward on the y-axis, free fall. The object is falling freely. So now I want to take you back to acceleration, what it means for an object to accelerate. So first of all, let's go to my screen. So now I have an object sitting here in the air, just sitting in the air. I'm holding the object. But of course, as soon as I let go, that object begins to fall. And of course, it's falling downward. Now, when it falls downward, it actually accelerates downward. It has some initial velocity. While I'm holding it, of course, it's 0. I'm just holding it. Then I let go, and it begins to fall. As it falls, class, it accelerates under the influence of gravity. So there's a force of gravity that's pulling it down. So we call this value, we're now going to use G, where G simply stands for the gravity that causes the object to accelerate downward, the force of gravity. And that particular value is a constant. So whenever you see G, or you may see A sub G, means acceleration due to gravity, or you just may see A understood to be gravity. Now, in that case, that value has a magnitude of 9.8 meters per second squared. That's the SI unit. What that means then, class, is that this object is at rest, but after 1 second has passed, 1 second, which means that it's accelerating downward at 9.8 meters per second every second. So that means then if I will watch this object fall, after 1 second has passed, now it's moving at 9.8 meters per second. If I wait and watch it speed up, 2 seconds later, now it is moving 19.6 meters per second. Because what's happening is every second that passes, its speed increases by 9.8 meters per second. That's what it means. It's accelerating constantly. It's constantly getting faster by 9.8 meters per second every second. So that when 10 seconds has passed, we know I can multiply this by 10. So it means 10 seconds later, the speed 10 seconds later is now 98 meters per second, because 9.8 times 10. That's what it means. So I hope you understand now what is meant by constant acceleration free fall. But not only is it increasing in its speed, because it's moving downward, this is a vector pointing downward. So when I say magnitude, what I mean is how much is the value of it without the sign. But in reality, this number is negative. This number is negative. This number is negative only because of the direction, because it's moving downward. But the magnitude of it, of course, is 9.8 meters per second. Now, let's put that value on our equation quiz. So let's do that very quickly. Let's go to our original equation quiz here. Now you notice we've put almost everything on this sheet. So now we're able to go to number 26. And I say, what is the magnitude of acceleration due to gravity? And sometimes we use the symbol G for that. So we say right here that G is 9.8 meters per second squared. That's the magnitude of it. Now, it says, what is that same value in the US customary system units? So by that, I mean to convert this number to feet per second squared. So of course, let's just do a quick conversion here. If I have 9.8 meters per second squared, but rather than having second squared, I don't want that. I want to have what? I'm sorry, forgive me. Forgive me, I'm not saying that. Okay. What I'm saying is I don't want meters, I want feet. And I know that 1 meter is 3.281 feet. So when meters cancel out and I multiply this, I will get that G is also 32 feet per second squared. So those are the acceleration due to gravity values. Now, let's go back up to our equations we were filling out earlier. And we said, what is the displacement with acceleration? So we said that is x, which is v initial times t plus 1/2 a t squared in meters. Now watch this. This is very important. Now take the same equation, but rather than being along the x-axis, I'm on the y-axis. Here's my object right here. It's going to fall down. And my initial speed is 0. It's just sitting there. I haven't dropped it yet. So that means then, of course, that v initial is 0, then this whole term is gone. So now the object is falling. So it falls from here to here. The object falls. Initially, 0. Then at the bottom, when it hits the ground, it's going to have some final speed, but it falls under the influence of gravity. So I can find the height that it falls simply by knowing that now this height on the y-axis, is what I call the height. So from this equation right here, what you can see then, class, is I can have an equation for height being a scalar. Height is 1/2 is falling under the influence of gravity. So I know what that number is. That number is going to be 9.8 meters per second squared. So I'll just call that G, T squared. So you notice then that if an object falls free, that's what free fall means. Then of course we have an expression for finding the height. So now I want to go back to our equation quiz, our kinematic equations, and write all the equations in terms of y. Okay, so let me go there. Now I had a question from someone. Did someone have a question about not getting the quiz? Did someone say something about the quiz? Go ahead and speak, please. I saw a message come up, but I'm not in my email right now. That's why I'm not able to do that. Okay, let's go back now to where we were with our PowerPoint presentation. Okay. Now, these are the equations for kinematics along the x-axis. So that means that everywhere I have x now, everywhere I have x, I can replace that with y. And also, wherever I have a, I can replace that with g. So in your notes now, you can just write that. So let's go here. Let's go to new share. Hold on. Okay. Now, these are my equations. So all of these so far, we'll say that these were on the x-axis. So now let's go to the y-axis. The same equations, but now I'm going to talk about the ones on the y-axis. And if you've been studying these equations, you should have them somewhat learned by now. So on the y-axis, on the y-axis, same equations. So we say y is 1/2 v initial in y, because we're talking about y now, plus v final in y times t. This t we're going to learn in next chapter is the same in x or y. So now I don't have to put these subscripts here. I'm just trying to show you that this is the same equation, but now I'm talking about what? Along the y-axis. But I don't need to have those y's because you're going to know that you're talking about the y-axis, so you don't have to have that. That's what it means though. So now we have that equation. Or we can say that y is v initial times time plus 1/2. And now I know that a is g t squared. This is in free fall. Or I can say that v final in y is v initial in y plus acceleration times time. And then finally, I have one that says okay. Oh, goodness. Hold on. Okay, I cannot find where I'm supposed to go. Let's just move on now because my time, I cannot believe I'm so short of time. Okay, let me show you this page. What do you all see? Do you all see the equations for kinematics? Okay, great. All right. Okay. Now, let me review this. This is so important, especially for the exam coming up, the quiz coming up. Make a drawing. Decide which directions are to be called positive and negative. Remember, going to the right and going up is always positive. To the left and down is always negative. Write down the given. Make you a chart and then identify what is given. So you have either the displacement, we're going to be talking about y now. So displacement, acceleration, which is always going to be negative 9.8 meters per second square on the x-axis. I'm sorry, on the y-axis, please forgive me. Then you have the initial, which is often 0, but not always. Then you have the final, and you have the time.
Are
So
you
that's what we're going to be working on
writing
going
anything
forward.
down?
Yeah, you can't see that?
No, ma'am, I can't.
Oh, no. Okay, hold on. Okay, forgive me. Let me just see. What do you see? Do you see the board?
No, I see the kinematic equations for constant acceleration.
Okay. All right. Well, let me just go on. Do you see the example 2.5?
No, ma'am. It's in the Word document, equations quiz 2.
Okay, hold on. Let me just share screen. What do you see now?
The PowerPoint.
You see 2.5?
Yes, ma'am.
Okay, great. Okay. Well, unfortunately, class, I need for you to study those problems yourself because I really have to get to this next section. So, freely falling bodies. So I've already told you that in the absence of air resistance, that means that the only force acting on it is just the force of gravity. It is found that all bodies at the same location above the earth fall vertically with the same acceleration. If it's small, the distance is small, close to the earth, these are the values that you see here. I've given you these values already. So this idealized motion is called free fall. And the acceleration of a freely falling body is called the acceleration due to gravity. And that's why we use this symbol G. Okay, now this is very important. If I have air in this tube, then you notice the heavier object, like a rock, will fall more with a higher speed than a lighter object that's blown around, say, by the air. But in this evacuated tube, in other words, if I ignore air or remove air, then the boulder and the paper, a light object and a heavy object, falls at the same rate. Only have one value. Doesn't matter how heavy it is or how light it is. This is my constant value for freely falling bodies. So we have an example. A stone is dropped from the top of a tall building. After 3 seconds of free fall, what is the displacement, y, of the stone? Now, this is a very good example for me to start with because here you see they're looking for the displacement. And the displacement is a vector, not like the height. The height is always a scalar. So now let's follow the rules we just went over. Write down. Now, can you see me write on this board? Do you see this? Yes or no?
Yes, ma'am.
Okay, good. A stone is dropped. That word drop means that the initial speed is 0. If it's dropped, it also is under the influence of gravity. So my G, of course, is negative 9.8 meters per second squared. Okay, here we are. Now, after 3 seconds, that means my time is 3 seconds. And it says, what is my value for y? In other words, what is my displacement? So remember in our strategy, we said if I have 3 of the 5 things given, there's an equation. And of course, you notice here that the equation I want to use is the one that does not give me the final speed. I don't know what that is, right? That's not given. If I don't know that, then I can't use that equation. So immediately then I think about my equations and I say, now which one has initial velocity, acceleration, and time? And I'm trying to find y. And I said, oh, well, y equals v initial times t plus 1/2 a t squared. And a, I know, a is what? A is g. Vi is 0, so that whole term is gone. So I have 1/2, acceleration is g, negative 9.8 meters per second squared. T is 3, 3 squared is 9. So I got 9 second squared. Second squared cancel out. And when I solve that, I'm going to get some number that's negative. Okay. So here we have, again, we solve the problem and we get negative 44.1 meters. Now, this same question could have been asked of you differently. It could have said, a stone is dropped from the top of a building. What is the height of the building? And of course, we know to find height, we say 1/2 gt squared. And you may be wondering why this g is not going to be a negative number. And that's because height is the magnitude of a height must be a positive number. In other words, when the object was falling, the displacement is y. But the height means I'm measuring it from the bottom up. You see, when I go up, when I move up, we said that up is always positive. So height is always a positive number. It's the same number. In other words, if I ask you to find the height of this building, I would still say that this building has a height of 44.1 meters. So that's the displacement, but the height is positive. I want to make sure I point that out. The height is positive. Okay, next problem. The referee tosses the coin up with an initial speed. So now identify again what's given in the problem. The initial speed is 5 meters per second. And you see, if the object is going up, it has to have initial speed. But of course, the question says, how high does the coin go above its point of release? So the maximum height that it can go tells me that once it gets here, the final speed has to be 0. Okay, now it appears that not enough is given, but we know that the problem is under the acceleration due to gravity. In other words, how did the speed go from 5 meters per second to 0? Something is slowing it down. And of course, the force of gravity is slowing it down. At what rate? At a rate of negative 9.8 meters per second squared. So how high above the, how high does the coin go? Okay, so we're still looking for what? We're still looking for y. We want to know along the y-axis, how high did it go? Oops. Okay. So now, hold on. How high does the coin go above its point of release? That's what I'm looking for. What's not given in the problem? Time. So now I've got to choose the equation that doesn't give me time. And of course, the equation that doesn't give me time is this equation, which I rearrange to solve for y. Once I rearrange it, then I plug in the values. Plug in the values that are given, I find y. And you notice now in this case that y is positive because it says how high above this point of release did it go? And of course, it has to be what? A positive number. Now, let's talk about the next assignment. In your email, I sent you another assignment. So let me turn to that quickly. Okay, let me try to find it. Hold on. Do you all see the assignment in your notes? Do you see it? Because I don't have it on my board just yet.
Did you recently send it in an email?
Yes, it says chapter 2, assignment 2, student copy. You should, I think I found it. Hold on. Well, I can't seem to find it on my, let me go here and close out some of this. Hold on. Believe me, teaching from this screen is not easy. Okay, let me try to share. New share. Okay, do you all see that? Number
Yes.
1? Okay, so that's what I sent you. All right. Ball A is dropped from rest from a window. At the same instant, ball B is thrown downward and ball C is thrown upward from the same window. Which statement concerning the balls after their release is necessarily true if air resistance is neglected? And the only thing that we know is true, class, is that they are all under the influence of gravity, okay? So we look for that, okay? All 3 balls have the what? Same acceleration at any instant. That's the one thing that is true for all 3 of these balls. So they can't strike the ground at the same time. They don't have the same velocity because one was thrown down, which means it has initial velocity. They don't have the same speed, but they all are under the influence of gravity. So we're going to choose D. Okay, I'm going to choose D. All right. Okay. Now, a ball is thrown vertically upward from the surface of the earth. Consider the following quantities: the speed of the ball, the velocity of the ball, the acceleration of the ball. Which of these is or 0 when the ball has reached its maximum height? So if I throw a ball up, when it gets to its maximum height up here, then the speed up here and the velocity up here, both of those at the very top have to be 0. What is not 0 is the acceleration, because the acceleration is always constant, 9.8 meters per second squared. So my answer then is the speed and what? And the velocity. So that would be what, class? 1 and 2 only. Will be 0 when the ball has reached its maximum height. Okay. Let's move on down to a problem. Let's move on down to a problem like number 4. So let's make sure we understand how to set the problem up. So the first thing you do is identify what is given. A brick is dropped from rest. That means the initial speed is 0. From a height of 4.9 meters. So now this is my height. It is 4.9 meters, but that means though that y now is negative 4.9 meters. And you say, why is it negative? Because if it's dropped from a height of, that means that I'm looking down. My object is moving downward. So anything that points downward, we said is negative. How long does it take the ball to reach the ground? So I'm looking for time. Now, this looks like 2 things given, but these are actually 2 of the same. So I really only have 1 thing here that I know, 1 thing here plus this. So I need to know another variable, which I do. I know the acceleration. I know that it's due to gravity. So I say what? Negative 9.8 meters per second squared. If I saw this equation for height, if I use the equation that says h is 1/2 gt squared, then just keep in mind that this g is positive. If I want to solve the equation that says y equals 1/2 gt squared, now I'm talking about the displacement, then I put in a negative value. But either way, I'm going to get the right answer. Okay, I'm going to get because it says that how long does it take the brick to reach the ground? And the important thing is I'm looking for time. And if you remember from our last lecture, time is always a scalar. So time can never, ever, ever be negative. So if I'm solving for height, I cannot put a negative number here. But if I'm solving for y, I can't put a negative number here, and negative here will cancel out. So time will always be positive. Make sure you understand how that is explained. Okay, you can go ahead and finish that problem later. I want to move on to another problem. Okay. Let's look at number 5. Kirsten, turn it off for me, please. Okay, number 5. Again, you notice how I always start the problem in this manner. Before I even read the problem, I'm going to identify what is given in the problem. A ball is dropped. Initial velocity, 0. From a tower and strikes the ground below 110 meters. So then that means that my y value is negative 110. Approximately how many seconds does it take the ball to strike the ground? I'm looking for time. Neglect air resistance, which means that my value for A is negative 9.8 meters per second squared. I can find the equation that doesn't have V final and solve for T. Okay. Hope you understand what I'm doing. All right. Let's just move right along. Now, I've already gone through the first 5, and I've only given you, I think, 16 problems here. So that means then that the rest of these problems that you should be able to work on your own, which I don't see why you would have a problem working them out, because now you can see what is the standard way to work them out. Let's look at number 9. A hammer is accidentally dropped. Remember, we said anytime it's dropped, the initial speed is 0. Okay, from rest means it's 0. Down the vertical mine shaft. How long does it take for the rock to reach a depth of 79 meters? Again, Y now is negative 79 meters. We're looking for time. Again, it's under the influence of gravity. So A then is negative 9.8 meters per second squared. I can solve for time. So you notice, class, that these are actually the exact same problems as on the x-axis, but actually a little easier, because now we know the value for A, which is a constant, is always negative 9.8 meters per second squared. So that is what you're going to work on for the remaining of this assignment. Okay, let's look at some of these others. Just make sure I haven't done anything different in some of these. Okay, let's look at number 11. A ball is shot straight up from the surface of the earth. So that means now that my initial velocity is not 0, because it's shot straight up with a speed of 19.6 meters per second. Now again, it appears that not enough is given, but we know that anytime it's shot straight up, it's under the influence of gravity. So I know the value for A, which is negative 9.8 meters per second squared. You see how I keep saying that? Because when I continue to say that over and over again, it then becomes stuck in my mind, and I know it. So this one says, what is the magnitude of the ball's displacement from the starting point after 1 second has elapsed? So now my time is 1 second, and it wants me to find the displacement. In other words, what is y? Okay. What is the magnitude of the ball's displacement from the starting point after 1 second has elapsed? A ball is shot straight up. I'm looking for y. So now, what is my equation? Again, V final is not given, but in this case, do not be tempted to put V final as 0 in this case, because see, it didn't say that it had reached its maximum height. It just says, what's the displacement from the starting point after 1 second has elapsed? Then the next question says, what maximum height will the ball reach? Now, in this case, I know that V final is 0 because it has reached its maximum height. But in this case, I do not. I want to just know how far has it gone? How far has it gone up after 1 second? So you see the difference in that? Then number 13 says, how much time elapses between the throwing of the ball and its return? So this time now is the time total. In other words, what you could do is find out how much time it takes to reach its maximum height, which is 0. Hold on. Okay. It reaches maximum height, that's 0. The initial is 19.6. So an A is negative 9.8. So I can find the time here. In other words, the time it takes to go up. And once I do that, I can just double the time, because now I want to show you this. It's called symmetry. What goes up must come down. And it goes up, we call that time up. It has to come back down, we call that time down. So the total time would be twice time up. So look at that when you solve that problem. And then finally, you have 3 problems where very similar problem. So I think you can solve all of these. So this section that we just covered here allows us to almost complete chapter 2. If you look on your outline though, we're already getting behind. And when I say getting behind, I'm only referring to the outline that I gave to you. So let me do a little housekeeping now. This is very important. Let me do a little housekeeping. I talked with the other professors because they are also challenged, as we are, with trying to cover so much material in such a short, abbreviated time. In other words, through no fault of our own, the system gave us less time than what we should have been allotted. Actually, class, we're supposed to meet for 2.5 hours each day, which is what we do. We do 2 hours in the normal session 3 times a week, but for some reason it's not that way. So we are really impacted with this reduced time. So by housekeeping, what I want to do is I want to know, am I moving too rapidly? Am I covering too much material too quickly for you to be successful? So let me go here to my chat and see what's going on now. Okay, chat. I need to have okay, I've been missing my chat because see, the reason why I don't go back and forth to chat class is because again, that takes a lot of time. I have to be able to move back and forth. And as you can see, I'm having difficulty even keeping up with my screen sharing. But if you can just come off chat and speak, then I will be able to hear you. I can hear much better than I'm able to go into chat. Okay.
Yes.
So now my question to you is, okay, Kaylin, thank you very much. The question I'm asking is, do you think that I am moving too rapidly through these lectures for you to be successful? That is my question. You want to tell me privately, you can, or you can just tell me, just put it in chat so I can have this as a reference point. I need to have a reference of how the class is going. Because see, unlike when we're face to face, this is a very a benign environment. I can't see you. I can't see your papers. I can't come around and see what you're writing to see if you're doing it correctly. So I need to know if you are understanding. So Kaylin, if it's only you, then we can find some time to do one-on-one, because so far only Kaylin has indicated that it's a little fast for her. Okay, so I will assume that all the others should tell me no. In other words, I need to hear from you. Am I moving too fast through the lecture? Okay, Morgan says yes. Okay, then you says yes, I'm moving too fast. Okay, how about the others? Morgan, Kendra. Okay, so everybody say now, that's what I'm talking about. Okay, great. That's what I need to know. I need to know if the lecture is at too rapid a pace. So now that means then that I can plan to slow things down. Okay. Now, this question from Nigel. It would be nice if the homework was due every other day. I understand that. That's one of the things we discussed. I discussed that with the professor who's teaching calculus-based physics. And he and I both agree that in the normal semester, the regular spring and fall semester, we almost always have a day between the lectures. So you have, if I meet on Monday, that assignment is not due until Wednesday. However, and unfortunately, we do not have that privilege because the material that I need to cover, say tomorrow, is based on your understanding of the material that I'm covering today. And once I cover it today, I need to be able to have some response from you to see if you are understanding. So, Nigel, what I have done is these multiple choice problems I'm giving you, I am labeling these as assignments, which means that if you turn in anything, then you will get credit for having done the assignment. Then I give you a little more time, a day or two in between, for the homework. So if you notice, then what I just gave you was considered an assignment, where I want you at least just to try one or two. See if you understand it. I went through several of those, trying to set them up for you. So now you can just go through a few of those. And if you turn in the assignment, that will give me an opportunity to see what I need to cover more thoroughly, say the next time. So the homework that I'm going to assign to you today, I am going to assign it today. I'm going to make that homework due on Wednesday. So that actually covers what you just said. The homework should be due. And in fact, if you look in your course syllabus, I've already given you the homework. The homework is already, the numbers for this assignment, this homework from chapter 2, I actually have those problems in Blackboard on the course syllabus and what I sent to you. So you have time for those. You could have already started those even last Thursday, because those are already given, but I didn't make you aware of it. So now I am. And if you need more time for the homework, say if you can't get it done by Wednesday, just let me know. If you have other classes or you're working or something is going on that you can't get that done, then you let me know and I will try to make some adjustments. Okay, the other item is when we have quizzes. So class, good news for you. The quizzes will almost always come directly from the assignments. So that means then that they're multiple choice, and the quiz that you have coming up now is from the assignment from chapter 1. What was that now? Chapter 1. I gave you the key back. So I've taken those very questions and I've simply changed some of the values for a few of those. Because when I grade your assignment and I go over it, then I feel pretty certain that you can work those problems. Okay, Kaylin, when we submit our homework, can you respond to us so we know that you received it? Okay, yes, I'll try to do that. I'll try to respond to say, got it. But for the most part, if you send anything through email, I receive it. And I haven't had a problem receiving anything that you sent via email. Even if you ask me, did you receive it? I can just tell you yes, but yes, I'll try to do that. You see, this class is small. That's a good thing. And I don't always respond. I just take it and put it in my save file, but I will try to do that as well. Now, in Blackboard, I have already designed a quiz, and you will have an hour to do the quiz. Now, that hour can be anytime between when I post the quiz. I probably have it posted by 3 o'clock and 1:30 tomorrow. The only thing is, once you start the quiz, you have an hour to finish it. But that hour can be any hour you want between now, well, when I post it, and tomorrow at 1 o'clock. So if you have to go to work, you have to do anything else, just say that, I have an hour to do this quiz. If I were you, I would look at my assignment from chapter 1 again, make sure you understand how to solve those problems. And that way you won't have any difficulty. You probably can finish this quiz in about 20 minutes. Okay, the only other thing about housekeeping is, if I don't tell you each day to sign in, please, when you first come in, sign your name so that I can give you extra credit for being on time if you're here before 1:35. And then when I end the class, before you log out, I need for you to sign out. Sign your name again in about 5 minutes, so that means you're exiting, because I'm giving extra credit also for those who remain in the class throughout the session. Now, that doesn't mean that you can just come back at 2:34, because I'm going to ask you, can you please sign your name? And that's what I want you to sign within a few seconds of hearing that. That means I know that you were here and you heard me when I said it, as opposed to running back at 2:35, because I'm just trying to encourage you to be a part of the class. Be a part of the class so that you don't miss out on important things that I'm saying. Okay, now, how's it coming with you all getting your textbooks? Have you all ordered your textbooks? Yes or no? Okay, very good. Monier. Okay, Kaylin. Okay, Nigel. Okay, very good. Now, I know that sometimes a textbook can be seen as a expense, but once you've paid for the class, once you've paid to be in the class, believe me when I tell you that the purchase of textbook now shouldn't be a cost that you're considering not doing, because once you've paid for the class, and I'm not sure what this 5-hour class costs, but it's pretty expensive. You don't want to risk failing the class by not purchasing a book. Now, the textbook can be purchased in a used book. I do not mind if you get the 10th or 9th edition, just so you have something you can read for yourself, so that you can go through all the examples, so you can see the pictures, so you can see the annotations and all the other figures that the author gives that better explains what we're trying to cover. Because again, an hour and 15 minutes, we're really being pressed to go through this material. Now, some sections I'm having to omit. So the last few frames in chapter 2, I would like you to look at those, but unfortunately, I will not have time to cover those. Let me show you what I mean with that. Hold on real quickly. Okay, do you all see the problem on the board, on the screen? Freely falling bodies? Okay. Okay, so look at this section, graphical analysis. So what the author wants you to look at when you see this, that actually the slope of a line. So I'm going to review this for you. We said that slope is rise over run, or the x component over the y component. Okay, so delta x by delta t, and we've already defined that as being what? Speed. So actually, you notice then that the slope of this line is going to be the speed. Then, let me see. Okay. What about acceleration? Okay. Acceleration also can be considered in graphical analysis because we say acceleration is the change in speed over time. So when we do that, we have the change in speed over time and we get the acceleration. So all we're showing here is that there's a graphical analysis of velocity and acceleration, which is just the putting it on a graph. So that's all that was about. So I didn't really spend much time on that, but you can look at it and I think that you will be able to understand it. Now in your notes, again, on the, let's see. Okay, hold on, let me. Give me a minute. Okay, class. So let's look at this page now. Let's share this page. Hold on. Okay, share screen. Here. Okay. So if you look here, I'm moving through. You see where it says freely falling bodies. So this is end of chapter problems. So of course we didn't get here in chapter in week 1. So we're actually in week 2, but the assignment for this, now this one you can ignore. This was chapter 1. You can ignore that. I gave you a few problems. But now I'm beginning to use the assignment that I'm giving you in the textbook. So end of chapter problems means at the end of chapter 2, we have 1 through 10 odd, then 13, 14, 15, 16, 17, 18, 19 odd. Oh, I'm sorry, those are odd too. Okay, so 13, 15, 17, 19. And then the even ones through 30. Now that appears to be quite a few problems, and they may be. But the thing that I want you to do is have enough problems to actually practice how to solve these. So even if you're not able to attack all of these, and even if I'm not able to go over all of these, I really need you to look at the homework, work on the homework. The homework actually has examples. They refer you back in the text which problems are like those. So look at where we are. We just finished freely falling bodies. So we have finished all of these topics. And so therefore I'm assigning this homework. Ignore this homework in the first field here. Start here. So we'll go over some of these problems. Even though it's homework, I'm going to go over a few of these at the beginning of next lecture. And then we're going to move into the next chapter, kinematics in 2 dimensions. This is chapter 3. So now we're ready to move forward. So class, at this time, I'm going to end the class. Do we have any questions before I ask you to go to chat and sign out? Okay. If not, now give me a chance to put it in first, because if I don't put it in first, then I'm not able to see your name afterwards. So let me find my, I don't even see it. Hold on. I don't even see chat. Oh, there it is. Chat. Okay. So give me a minute, please, to write my message. My message, type message here. Okay. So this says sign out. Sign out in chat. Okay. Okay. Enter. All right. Now, when I see your name after that, that's when you get the extra credit. Okay. Very good. Okay. I tell you.